Alright, grade 10s. So, well, natural science grade 10s, physical science grade 10s. Today we're talking about orbitals. I'm not going to pretend that it is my area of expertise. So what I've decided to do is I'm going to get a friend to explain to you and compile a little video, and you will look at it, and then we're going to see how you feel and we'll answer questions. So I'll chat to you in 15 minutes. Please concentrate and write notes, and I'll send you a recording so that you can then pause whenever you need to and review things if you have to. Okay, love you.
Okay, so this tutorial is about orbitals. We're going to look at what orbitals are, what they represent, how electrons go in orbitals, the order that they go in orbitals, and the shapes of orbitals. So we know that atoms are made out of electrons, protons, and neutrons. Electrons are very important. The arrangement of electrons really dictates how atoms will interact with each other. But we don't really know where electrons are inside an atom. We can define areas where they are with some high probability, but we can never really know exactly where they are. And so we define these areas as orbitals. Orbitals are areas within atoms where there is a high probability of finding electrons. And it is high probability that is the operative idea here. We don't know where they're going to be all of the time, but we know where they're going to be 90% of the time. That's what's meant by when we say the probability. These orbitals are probability clouds. Let's talk, before we go any further, very importantly about the word orbitals. It's an unfortunate word. It comes from the word orbit, which came from Bohr's idea that electrons orbit the nucleus like planets orbit the sun. And we know that electrons do not orbit the nucleus. And so the word orbitals is often something that can create a misconception with students. It makes students think that electrons orbit the nucleus, and they do not. We only can know with a certain amount of probability, 90%, where an electron might be, but not the path that it's taking. And that comes from Heisenberg's uncertainty principle. And as I said, this is important because the arrangement of electrons determines how atoms interact with each other. Schrödinger, building on Heisenberg's uncertainty principle as well as de Broglie's idea that electrons can act as waves. He created a mathematical model that described these orbitals inside an atom, these shapes, these high probability clouds. But we cannot know precisely where the electrons are inside the orbitals. And again, that comes from Heisenberg's uncertainty principle. So the area where the electron can be found, the orbital, as we just said, is defined mathematically. But we can see it as a specific shape in three-dimensional space. So we're going to take a look at that three-dimensional space. We're going to define it with the three axes x, y, and z, the intersection of which will be our nucleus. So our first orbital is going to be the 1s orbital. And what we're going to do now is take a look at the shapes of orbitals and what they're called. They're always designated with a number and a letter. And the letter designates the shape, and the number designates the energy level. So the 1s orbital is the lowest energy orbital, and the electrons in the 1s orbital are the lowest energy electrons. The problem is orbitals can only hold a maximum of 2 electrons. So if we were talking about helium with 2 electrons, that would be fine. Helium would be happy with the 1s orbital. But what if we were talking about lithium? Lithium has 3 electrons. Where would the third electron go? Well, it would go in the next higher energy level orbital, which is the 2s orbital. Notice that we still have an s orbital, and we still have a spherical shape. But the electrons in the 2s orbital are higher energy, and so therefore on average they're going to be further from the nucleus, which describes therefore a larger shape, a larger area that they're going to occupy. But again, this is just a single orbital. It can also hold 2 electrons. We still have the 1s orbital inside of it holding 2 electrons. So with the 2 orbitals we have now, we can have a maximum of 4 electrons. That brings us to beryllium. So beryllium is happy with the 1s and the 2s orbital. But what about boron? Boron has 5 electrons. Where is the 5th electron going to go? So as you may have guessed, we're going to go to another orbital, a higher energy orbital. And here, just to review, we have the 1s orbital that has 2 electrons. We have the 2s orbital that has 2 electrons. Don't forget, the orbital is the shape of the space where there's a high probability of finding electrons, 90%. S orbitals are spheres. What about that 5th electron? The 5th electron is going to start filling the 2p orbitals. So here we have a different shape. Here we have the p shape. And there are 3 2p orbitals. They're all oriented perpendicular to each other. So we have the sort of pinkish red on the y-axis. That's one orbital. Here's a second orbital along the x-axis, sort of a greenish yellow, I guess. And then the third 2p orbital along the z-axis. Now, each orbital, as you can see, consists of 2 lobes. So both lobes together constitute just one orbital and can only hold a maximum of 2 electrons. So we designate each individual orbital by the axis it's on. So here the 2p orbital will be called 2py, 2px, and 2pz. We cannot forget the orbital is the shape of the space where there's a high probability of finding electrons. And p orbitals, you could call them a dumbbell shape. They have 2 lobes. So let's say that 5th electron from boron goes into 2p. But what if we need to accommodate a 6th electron, which would be carbon? Carbon has a total of 6 electrons. Well, that could go into the 2pz orbital. And then what about nitrogen? The 7th electron that nitrogen has could go into the 2py orbital. But we said that each orbital can have a maximum of 2 electrons. So once each of these orbitals has 1 electron, then they can start to pair up and fill each orbital with a total of 2 electrons, and that would give the 3 2p orbitals a total of 6 electrons. If the p electrons are filling up, we know that the 1s and the 2s must also be filled up. So let's take a look at that. Once the 1s orbital is filled, we can then start to fill the 2s orbital, but again with only 2 electrons. Once 2s is filled, and remember 1s is still there, it hasn't disappeared, so 2s fills around the 1s. But now, once 2s is filled, we start to fill 2p. Again, the 2s, the 1s, they're still in existence, so therefore the p orbitals actually overlap with the 1s and 2s orbitals. So here's one of the 2p orbitals. Once another electron would come and fill this 2p orbital, another electron would come and fill this 2p orbital. Let's say all these orbitals are completely filled, and therefore we would have the 1s orbital with 2 electrons, we would have the 2s orbital with 2 electrons, and we would have the 2p orbitals with 6 electrons. How many electrons total is that? 10 electrons. What element has 10 electrons? Neon. So if all of these orbitals are filled up, that would be 10 electrons, and that would be neon. But what about sodium? Sodium has 11 electrons. Where would that 11th electron go? As you might have guessed, it would go in the next highest energy level, the next highest orbital, and that would be 3s. So 3s has electrons that have higher energy than any of those other orbitals we looked at, and so therefore the electron on average is further from the nucleus than the others, and it is larger than 1s, 2s, or 2p orbitals and surrounds them. So we can see the other orbitals still exist inside the 3s orbital, and the 3s orbital with sodium now is able to start getting electrons. So there's many more elements, and there are other orbitals as well. So let's take a look at the other orbitals. First, let's review. The s orbital is spherical. There's only a single s orbital at any one energy level. There's the 3p orbitals with this shape. There are 5 d orbitals, and this is their shape. So each one of these is a single orbital, and each one of these can have at most 2 electrons. So they describe what we're looking at. The illustration describes the outer boundary of that 90% probability of where the electron is going to be. So that outer boundary, that surface that we're looking at, that surface plus all the space inside of it constitutes the 90% area where we're going to find an electron in a d orbital. And then there's one more, the f orbitals, and there are 7 of them. Again, each one of these is a single orbital, and each one of them can have a maximum of 2 electrons. So the electrons can be anywhere. They're traveling 90% of the time anywhere inside these lobes. And if you track the electron long enough, you will start to see them describe these exact shapes that we're seeing here. One thing I think that students can get confused with is these shapes and what they represent, and especially when they get as complicated as the d and the f orbitals, and there's even the g orbitals that are even more complicated than f orbitals. So don't get tripped up by the complicated shapes. All you need to really understand is what they represent, and they simply represent space inside of which you're going to find the electron 90% of the time. So you don't have to worry about the specific shape so much. Just know what these shapes represent, where the electron is going to be. So finally, a nice way to look at that is this kind of schematic. Energy is shown increasing on the y-axis, and each orbital is represented as a circle. The circles don't represent the shape of the orbital, they're just representing the existence of the orbital. So at any one energy level, there's always just a single s orbital. And so the s orbitals, as you go to 1s, 2s, 3s, 4s, etc., they keep increasing in energy. As we saw before, 2p orbitals are higher in energy than 2s, and there is 3 of them. So the 3 circles represent the 3 2p orbitals. Not the shape, just the fact that there's three orbitals within the 2p energy level. The 3p energy level, again, p always just has 3 orbitals. But what about d? We saw before that there are 5 d orbitals. So at any energy level that has d orbitals, there's always going to be 5 of them at that energy level. And then finally, f orbitals, there's 7 of them. So any energy level that has f orbitals is going to have 7 of them, as long as there are electrons to fill those orbitals. The orbital does not exist unless the electron is in the orbital. So what, might you ask, does that have to do with anything? Why do we care about how electrons are arranged in atoms? Well, atoms are constantly interacting around you on the Earth and the solar system and the universe. Those interactions depend on how electrons are arranged in each atom. That arrangement, its orbitals, determine how the atoms interact with other atoms. If atoms did not interact with each other, would you be sitting here reading this? Probably not.
So I think that explained it to a certain extent, but it's always good to have a few different views, because remember, we all think in different ways. So I'm just going to include one more clip before we go through our questions, and you can tell me what you do and don't understand. And remember, NOMSA asked for detailed notes, so I'm going to send those as well, probably tomorrow morning. As you know, Saturdays I normally do bombard you with notes. All right, so let's see what this version is and if this helps.
And there are interesting places that have these very specific organizations and these interesting atomic interactions. They're quite popular.
Professor Dave here. Let's learn about quantum numbers.
He knows a lot about the science stuff. Professor Dave explains.
Now that we understand that electrons are both particles and waves, we are ready to learn about how electrons are arranged in an atom. The location and energy of every electron in an atom is determined by a set of 4 quantum numbers that describe different atomic orbitals. An orbital is a region of probability where an electron can be found. There are s, d, p, and f orbitals with different shapes, and they look like this. Remember, these shapes are not electrons, just regions in space where electrons can be, and each one can hold up to 2 electrons. The more electrons an atom has, the more of these orbitals it will need to accommodate them all. The first quantum number is the principal quantum number n, which can have any positive integer value. We saw this when we learned about the Bohr model. It represents the energy level of the electron. Each orbital will have an n value, and the larger the value of n, the further away from the nucleus it is. The next quantum number is the angular momentum quantum number, L. This can have any value from 0 to n-1. For example, if an electron has an n value of 3, it can have an L value of either 0, 1, or 2, because 2 is 3 minus 1. The L value describes the shape of the orbital. When L equals 0, we are describing s orbitals, which are spherical, just one of these per energy level. When L equals 1, we are describing p orbitals, which are lobes that extend outwards on 3 axes. There are 3 of these per energy level. When L equals 2, we are describing d orbitals, which are weird looking, 5 of these per energy level. And when L equals 3, we get f orbitals, which are even weirder looking, 7 per energy level. Next, we have the magnetic quantum number, m sub L. This can have a value of anywhere from negative L to L. So if L is 2, m sub L can be negative 2, negative 1, 0, 1, or 2. This quantum number determines how many orbitals there are of a type per energy level, and therefore describes a specific orbital amongst a particular set. When L is 0, m sub L must also be 0, and that's why there's only one s orbital per energy level. When L is 1, m sub L can have 3 values, which is why there are 3 p orbitals per energy level. An L value of 2 gives us 5 values for m sub L and 5 d orbitals, and an L value of 3 gives us the 7 f orbitals. The last quantum number is an easy one. It's the spin quantum number, m sub s. This one will be either 1/2 or negative 1/2, no matter what. So every electron in an atom has a unique set of quantum numbers. No 2 electrons in an atom can have precisely the same 4 quantum numbers, as is stated by the Pauli exclusion principle. This is because any orbital can only hold up to 2 electrons, and even the 2 electrons in the same exact orbital will have opposite spin values. So let's try to describe different sets of quantum numbers and what they mean. When n equals 1, L must be 0, and m sub L must also be 0. That means we are describing the 1s orbital. It can accommodate 2 electrons, which will have spins of half and negative 1/2, respectively. This is the lowest energy orbital, so any atom on the periodic table will fill this orbital first. The electrons in hydrogen and helium occupy this orbital since they have only 1 and 2 electrons, respectively. When n equals 2, L could be 0, which would give us the 2s orbital, or L could be 1, meaning m sub L could be negative 1, 0, or 1, giving us the 2p orbitals. The outermost electrons in the second row of the periodic table will occupy these orbitals. When n equals 3, L could be 0, giving us the 3s orbital. L could be 1, giving us the 3p orbitals, or L could be 2, giving us the 3d orbitals. A large atom will have to use all of these orbitals and more to house all of its electrons. The Aufbau Principle tells us the order in which an atom will fill up its orbitals. This is determined by their relative energies. Orbitals that are further away from the nucleus have higher potential energy, so it'll be 1s first, then 2s, then 2p, 3s, 3p, and so forth. We can use this to determine the electron configuration of any atom. For example, a neutral chlorine atom has 17 electrons. So looking at the orbitals, each of which can hold 2 electrons, let's fill them up starting at the lowest energy and then climb upwards. The 1s orbital gets 2 electrons, one spin up, the other spin down. Then the 2s, then the 2p's, then the 3s, and the last 5 will go in these 3p orbitals. Hund's rule says that for electrons of the same energy, you put 1 electron in each orbital first before doubling them up. So 1, 2, 3, 4, and 5 gives us a total of 17 electrons for chlorine. That means chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. The numbers before the letters are the n value for the orbital. The numbers after the letters tell you how many electrons sit in each type of orbital. If you want a quicker way to determine electron configurations, just know which areas of the periodic table correspond to which types of orbitals. This area is called the s block. This is the p block. Here's the d block, and then the f block. When we are determining the electron configuration for an atom of a given element, the easiest way to do it is just travel left to right and up to down on the table until you get to the element, since each element has one more electron than the last. Looking at chlorine again, the top row is just the 1s orbital, that's full, so 1s2. Going to the second row, where n equals 2, we fill the 2s orbital, which holds 2 electrons, hence 2 elements, the 2p orbitals, which hold 6, so we pass 6 elements. Then the next row down, we fill the 3s orbital. And lastly, we get to the 3p's and count 1, 2, 3, 4, 5, 3p5. A common abbreviation is to use the noble gas from the row above and list it in brackets. This would be read as neon core, and it implies the ground state electron configuration of neon. Then you just list the valence electrons of the element, or the ones that correspond to the row it is in. We can use orbital diagrams to visually depict how the orbitals are filled, and they look like this. Don't forget Hund's rule, fill each set halfway before doubling up. For a quick definition, atoms with unpaired electrons in their orbital diagrams are called paramagnetic and are attracted by a magnetic field. Atoms with all of their electrons paired are diamagnetic and are not affected by a magnetic field. So to summarize, N tells us the energy level, L tells us what type of orbital, M sub L tells us which specific orbital amongst a set, and M sub S tells us the spin. Each electron in an atom has a unique set of quantum numbers, and an atom will fill up orbitals with electrons according to the Aufbau principle until all of its electrons have a place to stay. This is a tricky concept, so if you feel confused, try watching one more time from the top. Otherwise, let's check comprehension.
Okay, so I'm in awe of those teachers. They're both so good. But we must use everything we have at our disposal to try to understand. And I'm sending you the video as I promised. But you must understand, hey, that this is Cambridge and a lot of it is going into A-levels and way, way beyond what you need to know. So if you do understand, wow, I'm proud of you, okay? I'm going to send you all the notes and we'll have a session next week and then we'll decide how we're going to make sure that you do understand and how we can do examples. And I might get Steve to also give you a lesson, okay, because he's a very, very well-renowned chemistry teacher. So thanks for watching. Bye.
Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.